Hi everyone, Ryan Angelo here again with my second project status update for our final project. My final project is on the displacement, stress and strain distributions in a A516 steel pressurized pressure vessel. Here is a quick overview of what I'll be going over in the second project status update. I will start by giving a quick problem description and then go over the one-dimensional studies that I did using Maple. And then finally I will go over the next steps that I need to take to continue developing the model for this problem. Here's my problem description. My problem is in regards to the stresses, strains, and displacements that occur on a A516 carbon steel pressure vessel. A couple of the mechanical properties of A516 steel are listed here. For grade 70 steel, the yield strength is 38 ksi, the tensile strength is 70 to 90 ksi, Poisson's ratio is 0.29. The modulus of elasticity is 29,000 ksi, and the density is 7,850 kilograms per cubic meter. For my problem, I will focus on the most common setup, which is just a cylindrical vessel with a rounded top and bottom. For one-dimensional studies, I used Maple. For my problem, the one-dimensional problem is the stress at a point on the vessel wall from one side of the vessel wall to the other. Just a piece of the thickness. For my problem, I chose a wall thickness of 2 centimeters. I don't have it written here, but the vessel radius to the inner wall is 1 meter. The internal pressure I chose is about 160 psi. This is comparable to a problem where the pressurized vessel would be storing compressed air. So using Maple, I was able to determine a solution via the finite element method and compare the results of that to the exact solution. For my finite element method, I used a mesh consisting of 16 elements. So a pretty normal size mesh, and the finite element solution and the exact solution gave nearly identical results, which you'll be able to see on the next page. Here is the graph of the exact solution and the finite element method solution plotted as functions of the radius r. As you can see, the two solutions at this resolution are nearly indistinguishable. So it's good to see that for this stage of the problem, the finite element method is giving pretty good and accurate answers to this problem. Now the next steps I need to take in developing my model after developing the one-dimensional model in Maple are to take that and use COMSOL to make two-dimensional and three-dimensional models. The two-dimensional model would just be the one-dimensional model rotated 360 degrees around the cylinder, so a cross-section of the vessel, whereas the three-dimensional model is obviously the entire vessel in 3 space. After doing that, a couple additional parameters that could be introduced that I would like to study further would be to introduce some thermal stresses, change up the vessel geometry, such as the shape of the top or bottom of the vessel, and also introduce an external pressure that would counter the internal pressure, so that it is not sitting at ambient pressure outside of the vessel. I don't know if I'll be able to get to all of these different types of problems, but I would definitely at least like to try a different vessel geometry and also introduce an external pressure outside of the vessel. So I will start studying those, and I'll see everyone in class. Thanks. Bye.